Do you ever wonder how some 3D printing materials, fingernail gel polish, adhesives, and industrial coatings are created? Let's take a look. Bomar Specialties is an American manufacturer of oligomers with a presence that spans worldwide. Headquartered in Torrington, Connecticut, Bomar is a lead innovator in the development of polyether and polyester urethanes for commercial use. Bomar is looking for new ways to optimize their batch reactor process by updating their process controls. Currently, Bomar utilizes 5 jacketed reactors to facilitate the heat-releasing reaction, relying on manual adjustments to the jacket temperature to maintain the reaction temperature. Taking a look inside the reactor, there is a mixture of chemicals shown in purple. Each system has a similar process setup, consisting of the jacketed reactor and a heat exchanger. How does this heat exchanger work exactly? Cold water is fed into this vessel, shown in blue, while hot steam is fed at the other end. When cold and hot collide, heat must be transferred, and therefore the cold water gains energy and exits warmer, shown in pink, and the steam loses energy, condenses to water, and becomes cooler, shown in orange. To prevent mixing the water and the steam is fed through the vessel as shown, while the water is fed through these smaller steel pipes surrounded by the steam. There are 2 main operations, heating and cooling. To heat the jacket fluid, a steam valve is open to allow the flow of steam, shown in red, into the heat exchanger. The jacket fluid flows into the heat exchanger through a pipe shown in pink, is warmed from the steam, then travels to the reactor through the pipe shown in orange. The warm water flows through the jacket and warms the reactor. To cool the jacket fluid, the steam valve is closed and cold water is instead sent down through these pipes all the way to the reactor. The cold water flows through the jacket, cooling the reactor.
Back to the purple chemicals in the reactor from earlier. Inside, there is a reaction where small molecule building blocks join to form one larger strand of molecules known as oligomers. To begin the formation of oligomers, the reaction must be heated to facilitate the interaction between molecules. As the oligomer chain forms, heat energy is released, causing the reaction temperature to increase and ruining the oligomer consistency. To improve the oligomer consistency, this temperature increase must be controlled by cooling the reaction. The current process setup requires manual operations. Operators are tasked with observing the reaction temperature and physically opening and closing the steam and cold water valves to maintain reaction temperature using the buttons shown. This method can result in significant fluctuations in reaction temperature, resulting in hotspots within the reaction. Hotspots form primarily in the center of the reactor, where the effects of the changing jacket temperature take the longest to reach. As a result, this section would take the longest to cool down and would negatively impact the oligomer consistency. Along with lower product output, this overheating may also produce some hazardous conditions, which may put nearby operators at risk of injury. So what's the solution? The automation of this entire process using technology. To implement this automation, we designed a feedback control system where a temperature transmitter would read the reaction temperature and sends an electrical signal to the steam or cold water valve to either open or close, given how the reaction temperature varies from the desired value.
We modeled this control using MATLAB to simulate oligomer reactions. This graph shows concentrations of reactant molecule building blocks and the oligomer product. Here, the graph on the left shows fluctuating temperature of the reactor contents over time while using manual control, while the graph on the right shows the not-so-fluctuating temperature over time while using automated control. We also compared the heat duty between 2 simulations and concluded that there was a smaller heat duty, therefore less energy required for the automated system, because it was constantly being monitored, allowing for frequent and accurate adjustments, whereas the manual operation had infrequent and inaccurate adjustments. Switching to an automated control system reduces the operational cost. Less steam will be used to warm the reactor, requiring less oil to be used to create the steam. This will decrease the overall cost of one batch. Additionally, the control would result in higher process repeatability and better product consistency. Also, with less oil being burned to make steam, Bomar will emit less CO2 to the atmosphere, increasing the sustainability of Bomar's oligomer production process. We would like to thank our sponsor representatives, Bill O'Connor, David Robitil, Tim Colette of Bomar, for collaborating with us on this project. Additionally, we would like to thank our faculty advisor, Dr. Stuber, who provided us with guidance throughout this project. We'd also like to thank the University of Connecticut's Department of Chemical and Biomolecular Engineering and the School of Engineering for providing us with the tools to effectively complete this project.